meters in 1 angstrom meter. So again, I prefer this way. So they're the same thing. If you put that into a calculator, you should get 18. I'm not going to worry about decimal points, but you know you should get 1870 times 10 to the 10th meters, or 10 to the minus 10 meters. All right, so if we put that into our equation, we'll get the energy of a photon is equal to Planck's constant. So 6.626 times 10 to the negative 34, which is a constant we need to know. We need to memorize that. And then 2.998 times 10 to the 8th, which is the speed of light, which is another constant we need to memorize, divided by the wavelength. So 1870 times 10 to the minus 10 meters. So let me put that into the calculator and let's see what we get. And it's good practice for you to put this into the calculator too, because it can get kind of hairy with all the exponents and stuff like that. So 6.626 times 10 to the minus 34, 2.998 times 10 to the 8th, divided by 1870 times 10 to the negative 10. So I got an answer that the energy of a single photon is 1.06 times 10 to the minus 18. All right. So if this is the energy of a single photon, right this here, that's the energy of a photon. And earlier we said that if we take the total energy and divide it by the energy of each photon, we should get the total amount of photons that are in that laser pulse. So the last thing is just to make sure our units match up. So this is in joules and this one's in gigajoules. So we should go ahead and convert one of them to the other. I'm going to go ahead and convert gigajoules to joules. So I'll do that in red over here. So 750.3 gigajoules. Let's see. There is 1 times 10 to the 9th joules in 1 gigajoule. Pretty sure that's the conversion factor. Let me know if I made a mistake. And that would give you 750.3 times 10 to the 9th joules. So now all we have to do is divide. So 750.3 times 10 to the 9th joules divided by 1.06 times 10 to the negative 18 joules per photon gives us a nice number of, so let's see, 750.3 times 10 to the 9 divided by answer. So I got 7.06 times 10 to the 29th photons. So, yeah, that's that. And there's the work. That's exactly how you should do it on your take-home assignment, because I just looked at the take-home assignment, and the wording of the take-home assignment is a nitrogen gas laser pulse with a wavelength of 363 nanometers contains 4.25 millijoules of energy. How many photons does it contain? That's the question on your take-home assignment. So it's basically, as Soldier Boy would say, word for word, bar for bar, the same as what we just did. So hopefully that helps you out on that.
So we told you how to do the take-home assignment without actually telling you how to do the take-home assignment.
Exactly. Yeah. So, yeah. Sounds like a plan. And the next one is also pretty much the the same as what's on the second question on your take-home assignment. The take-home assignment says the minimum energy required to ionize sodium is 493 kilojoules per mole. What minimum frequency of light is required to ionize sodium? In this number 2 on the worksheet we're doing says the minimum energy required to ionize cesium is 956 kilojoules per millimole. What minimum frequency of light is required to ionize cesium? Again, copied the flow of Dr. Armand, word for word, bar for bar. Anyways, let's give y'all 3 minutes to work on this one, and we'll tackle that after this. So it's 2:47. Okay, it's 2:48. So we'll reconvene at, let's say, 2:51. Okay, so go ahead, try it out. See you in a little bit. What was your mentee?
We're gonna do some play Roblox. Phone almost crashed. So yeah.
Phone almost crashed. That sound like OD. Play Roblox.
All right, I got it.
You got this one, bro. Yep. 956. All right, party people. It's Rich's time to shine.
All right. Minimum energy required to ionize cesium is 950 kilojoules per millimole. What minimum frequency of light is required to ionize cesium? All right. Let's solve it out. So we'll start with what we're given. 956 kilojoules per millimole. And then I don't like this millimoles right here, so I'm going to convert it to moles. So we know that 1,000 millimoles are in 1 mole. But do we want moles here? What do we want instead? I mean, yeah, we do want joules, but what do we want? Well, we want to get this in terms of cesium, right? Some related to cesium. So 1 mole is 6.022 times 10 to the 23rd
Cesium atoms, CS atoms.
CS atoms.
So basically why he's dividing by Avogadro's numbers, because the number they gave us is the amount of energy to ionize 1 millimole of cesium atoms. But it's asking, the question's asking for the frequency of light required to ionize cesium, as in 1 cesium atom.
So to do that, we have to figure out how many atoms are in that millimole. How many cesium atoms are in that millimole? In that millimole that is ionized by 956 kilojoules. So by doing that, as somebody in the class graciously has stated, you do need to convert to joules. So 1 kilojoule is 1,000 joules. It shouldn't really matter because it's all math, but generally you do the top 2 unit first, but I just started with the bottom because started from the bottom, now we're here. I actually don't know why I just started with the bottom. I just did the problem. I guess that's what came to me first. Point being, it really doesn't matter. So 956 times 1,000 divided by 6.22 times 10 to the 23rd. That is time multiplied by 1,000. You do that and put it in your calculator, you should get 1.59 joules per cesium atoms. Times 10 to the minus 15.
It's a big difference.
Always remember to check your scientific notation. 10 to 15 joules per cesium atom. All right. So this is the amount of energy required to ionize 1 cesium atom. So now it's looking a lot similar to what we did with the light. All we're doing is instead of light, we're using cesium. So we can use this equation, E equals H times F, or E equals HC over lambda. Which one do y'all want to use?
Top or bottom?
Yeah, the F would be easier. So we'll use that one. And we're also not given a wavelength. So
Muhammad said bottom. Why? You want to explain why you might not want to use?
Yeah, so yeah, you don't use the bottom one because A, you're not given a wavelength. B, it's also a lot of variables for what you don't need because you could just solve for the frequency directly in the top one. So 1.59 times 10 to the minus 15. And this will equal, so the frequency equals the energy over Planck's constant, which is a number we memorized, 6.626 times 10 to the negative 34. And if we solve that out, we will get 6.626 times 10 to the minus 34. Solve that out, we will get an answer of 2.4 times 10 to the 18, 1 over seconds. Or this is the same thing as Hertz. Some guy named Hertz made this up.
Anyone have any questions on that problem? It's very similar to your take-home assignment, so hopefully that gets you through there and you don't have to use Che.
Really changing up the web address now, becoming more slick.
All right.
All right. So move on to the next one.
Wait, Kennedy says, what's the unit for H?
I'm glad you asked. So this is in joules, right? So our Planck's constant, in order to cancel out this and get 1 over seconds, our Planck's constant unit is joules times seconds. So it's a joule times a second. That's the units for Planck constant because the joules cancel out and you're left with 1 over seconds. So yeah, this is in units of joules times seconds.
All right, next problem. How about we give y'all 4 minutes or 3 minutes for the next 2 questions, because number 4 is just basically, you know what, I'll make it a multiple choice question.
All right, so let's do A, gamma rays.
Man, at least make it legible, man.
All right. Gamma rays.
Can't read it. It's all right. His TAs always tell him to make his handwriting more legible too.
They do not.
They do.
Infrared. All right, let me just put IR, actually. Less letters.
IR is very important when you get to organic chemistry. Get
IR, C, radio waves, D, ultraviolet, E, NMR, F, none of them.
You have to do something with IR spectroscopy for the lab, right? Jen came up.
We did. It gave us the printed paper.
The aspirin? Is the aspirin one?
No, but like you have to interpret the IR, right? You have to read it.
I'll go look with that. We'll look at so many questions when the time arises.
Good. Dang, you're a lab partner. Got their money up.
Well, I was doing the ferric chloride test. She was doing that.
Oh, I see.
Because he told us to.
Oh, dude, that's crazy. Because like back in the day, everyone was tripping on the IR.
Yeah, now I see it. I'm like, bro.
You realize IR, GC, like the skills for that, mass spec and NMR is all stuff you can put on your resume, or not resume, your CV for skills.
No.
That's what Aguilar said at the UCS meeting. He's like, y'all know how to interpret an IR, right? That's a skill you can put on your CV.
Oh, my IRs are generated no chem lab. I actually put that as a skill. Probably not my IRs.
Yeah, you're right. Bad. Mind if I take a hot seat?
Oh.
All right. Sounds like we need more time. What you lost about with what is the wavelength? And you're given a frequency. What formulas do you know? Well, there's one extra one that incorporates one of the other, like that is incorporated to make one of the other ones. Because this is
that's sort of the why behind we use one of the formulas.
E equals H times F. You can derive it with another formula to make it into E equals H times C over lambda, where clearly F, if H stays constant, that means F is equal to C over lambda. But that's the speed of light, yeah. So,
and there's no such thing as a stupid question.
Unless your name's Rich. Rich got good questions all the time.
I've seen my fair share of stupid questions, and that was.
Yeah. I felt pretty stupid in no-chem. Especially because you took it over the summer. No, all right, time is up. Frequency equals, well, let's see. The equation we want to use is the one that incorporates the speed of light and how wavelength and frequency are related to the speed of light. Because this number is a constant, it's the universal speed limit. If wavelength goes up, that means frequency goes down. If frequency goes up, wavelength goes down. So that's one way to remember that formula. but we're asked to find the wavelength of microwave radiation, whose frequency is 1.258 times 10 to the 10th. Yeah, okay, that's right. E means times 10 to the 10th. All right. So we're looking for wavelength. So we should solve for lambda. So lambda is equal to C over frequency, where C is the speed of light. So if we plug in all of our stuff, we get 2.998 times 10 to the 8th meters per second divided by a frequency of 1.258 times 10 to the 10th, which the units for frequency is 1 over seconds, which is also a hertz. So 1 hertz. And if you put this into your calculator, you get this number 10 to the 1.358 is 10 to the 10th. Frequency of 2.38. And this is, or not frequency. This is going to give you a wavelength of 2.38 meters, which is pretty big if you ask me. When we look at something like cosmic rays, and their meters or their wavelength is like 10 to the minus 10 or something like that, something ridiculously small meters. Any questions on that one? So again, this one, relative to the other ones, this one's way easier. So I hope you were able to figure out what formula to use. And once you find that, it's really just a plug and chug. And that's honestly this, every calculation, this exam is just plug and chug. So next question, if there's no questions on that. Question 4 says, what form of electromagnetic radiation has the lowest energy of the following below? And what do you all say? Feel free to put it in the chat. C, Sydney says C. Do other people agree? Okay, so I think we can definitely say gamma and UV is wrong, right? And then IR and radio waves is the correct answer. IR is right after visible light, whereas radio waves is further down to the right of the electromagnetic spectrum. And so out of these, it's C. NMR is something you will learn in organic chemistry. It stands for nuclear magnetic resonance. And it's basically just a way you can determine the structure of any organic molecule or something, anything that doesn't have metals. You can determine the structure of it using NMR. And if you're really fancy and you got a crystal, you can use X-ray crystallography, which is what Dr. Armand does. All right. Are there any questions on 3 or 4? No, maybe so. Okay. Let's go to 5 and yeah, let's do 5. What is the wavelength of a neutron traveling at speed of 4.15 kilometers per second? Mass of a neutron is 1.675 times 10 to the minus 27th kilograms. So let's see, what are y'all thinking here? What is there an equation that we should use for this? Anyone know of an equation?
Starts with a D.
Yeah. Starts with a D. Ends with a E probably.
Quite.
Anybody? We went over this, or I know Dr. Armand went over this yesterday in class. If you were in class yesterday. Anybody? We also did a problem on it on Monday, I believe. Anyone? Does this give you the time and velocity one? Time and velocity.
Well, velocity is right. I don't think it has time though.
Yeah. So the something like the De Broglie, or I don't even know how to spell this guy's name.
It's L-E.
L-E. I-L-E?
Yeah,
De Broglie or De Broglie wavelength, basically. Yep. So this we did a problem like this on Monday for sure. It was the one with the baseball traveling at something like that. And I basically told you that anything that has mass has a wavelength. So for example, we have mass, but because our mass is so large, our wavelength is super small. So we don't see it. Or is that right? No, our wavelength is super large. I forget. Okay. So
our wavelength would be super small, we'd be bouncing around.
Yeah. So basically what this is the wavelength is equal to the mass or Planck's constant divided by the mass times its velocity now. So we realize that we have a really, really small value here, and we're really, really large here. Yeah, so our wavelength is super small. And we can go ahead and figure out the answer to this problem because we know velocity, we have the mass, and we know that Planck's constant is, well, it's a constant, right? So we know that. So make sure everything's in the right units. We never use kilometers per second. The SI unit for velocity is meters per second. If you've taken a physics class, that'll be pretty familiar with you because you always deal with meters per second in physics. So this is equal to 4.15 times 10 to the third meters per second. All right, and it's okay for kilograms. Kilograms is the SI unit for mass. So that's okay that it's in kilograms. So all we have to do is set that De Broglie wavelength equal to 6.626 times 10 to the minus 34. And we're going to divide by the mass in kilograms. So 1.675. 1.675 times 10 to the minus 27 kilograms. And we're dividing it by the velocity of the object as well. So that would be 4.15 times 10 to the third meters per second. And you should, if you put that into your calculator, you should get a nice number of 9.53. So 9.53 times 10 to the negative 11 meters. So that's the wavelength of a neutron in the center of an atom. Right, so number 6, are there any questions on this one before we move on? De Broglie. Remember, if you're ever asked for a wavelength and you're given a speed and you're also given a mass, you should probably think of De Broglie wavelength and that equation associated with it to the right of the name. This guy actually won a Nobel Prize. Pretty cool. He actually won a Nobel Prize because it was the original equation was h divided by momentum, and he said, well, look, that means anything with mass, because momentum is m over v, anything with mass has a wavelength. And they said, wow, you're a genius. So they gave him a Nobel Prize. But anyways, not that anyone asked. We can move on. This set of quantum numbers violates which following principles of quantum numbers? So I actually have something, we'll give you a little mini lecture. Let's see. All right. So let's see. You can tell the different handwritings here. Let's put it in mine here. So you want to give him the lecture, Rich?
All right.
All right.
Okay, so basically now we're going to go into something known as quantum numbers. So what they are is basically they tell you the address of an electron. So they give you like the precise coordinates of where an electron is located in like a given like atom. So obviously, right, there are rules to this, like you can't just live on the ceiling, right? So there are rules as to how quantum numbers, sort of work. One of them is something called Pauli's exclusion principle. So electrons in the same orbital can't have the same spin. What does that mean? So say, for example, you had two electrons, right? Every electron must have an upspin and a downspin. So like that, and like this. Well, I'm just gonna explain this. Like that, like this. This is the incorrect way to fill these up, but I'll show you the correct way in a second when we get to the bottom of this paragraph. Like that, like this. So if you have stuff like this, that violates Pauli's exclusion principle because both of the electrons are spinning upwards. Because like charges repel, right? So if they're both spinning the same way, that means they're both like moving the same way. So if they're moving the same way, they want to be farther apart from each other, which we don't want to happen. So fill them out like this. So spin up, spin down. That's basically what Pauli's exclusion principle says. So then Aufbau principle, this is related to the energies. So it's the specific order of which electrons are added to a subshell. So this is something like you fill the s orbital first before you fill the p orbital, before you fill the d orbital, or generally. So normally it's like s, p, but then there's some exceptions. Like when you get to the period 4, you fill in the d orbital before you fill in the p orbital. We'll go into that, all of that, once we touch on electron configuration. That's the next chapter. But just know that you can't, let's see, you can't fill in a higher energy orbital first because of Aufbau's principle. We'll touch on that as we get to electron configuration.
So it may not make sense to you right now, but typically when you start with your orbitals, it's always 1s2, and then you fill, I don't even want to write this as I say it. But yeah, it's like that little pyramid triangle thing. You always start with 1s2, and then you fill the 2s2, then it's 2p6, and then 3s2. I don't know if this is familiar from high school chemistry, maybe, but this is the order in which you fill the orbitals is Aufbau's principle, and it starts from the lower energy level. So the lowest energy level in an atom is the 1s orbital. So you always want to put the first electrons that go into an atom are 1s electrons. And then after that, once that's filled, it goes 2s, 2p. And you can actually just look at a periodic table and it'll kind of show you. Dang, he just wrote everything. Okay, anyways. You don't have to memorize this. You can actually figure it out by just reading a periodic table. So I wouldn't worry about that.
Yeah, I just did that to see like, because we were explaining before the S, P, D, and F. I just wanted you all to see that clearly. So like for the 4F, it's higher in energy than the 6S. So you'd fill the 6S orbital before you fill the 4F orbital. That's basically what Alpha's principle states.
Yeah, so you can erase all that, I guess. Just ugly for next semester.
Bonus points if y'all can tell me the element that this electron configuration corresponds to. I guess brownie points. All right, so then there's this other thing called Heisenberg's uncertainty. Heisenberg's uncertainty principle. No, this is not the chemistry teacher from Breaking Bad. It's you can't know both the momentum and position of an electron with certainty. What does that mean? So you can either tell where an electron is or how fast it's moving. You can't tell both because electrons, they move like really fast right around the nucleus. So you can either tell how fast it's moving or where it is. There's no in between.
Yeah, there's actually an equation for that. I'm not sure, it's right there. So the change in position and the change in momentum is greater than or equal to Planck's constant divided by 4 pi. And what this means is because everything on the right of the equation is a constant, if the delta x increases, that means the change in momentum or your certainty of the momentum decreases. So again, like Rich said, if you know how fast you're going, you don't know where you are. That's basically what the Heisenberg's principle says. Or if you know where you are, you don't know how fast you're going. And there's a couple of jokes on Reddit about the, Heisenberg uncertainty principle, but I'm not going to get into that right now because, maybe once we do more problems on this stuff.
Yeah, so this is where I was going before. The way I was filling in the orbitals was actually incorrect. This is the correct way to fill your orbitals. This is called Hund's rule. H-U-N-D, Hund. So each electron is placed in empty orbital before doubling up. So that's like saying what I was doing before. It was like that, like this, but that's actually incorrect. The way you should do it is put one electron here, then, this one's filled. So I put one here, and then you put one here. And then now you give everybody a name. So one over here, one over here, one over here. You do that mainly because if you put in, it's the whole idea of like, if you put in an electron in an orbital, like even one electron is considered occupied. So like, say for example, like you're going to, imagine like one of those like laboratories on like a plane. It says like vacant or occupied, right? So one person can only be in there at a time. Like if one person's in the stall, it will say occupied. So it's the same sort of situation with electrons. So if like it's occupied over here, you'll find like a different restroom. And if there's two people, I don't know what they're doing in that restroom, but you don't want to be in there. That's what we call it, super occupied.
Yeah, so it's like when you get onto a bus and you see one person sitting down in seat 1, right? You don't sit next to that person if seat 2 is open. You sit in seat 2 because you don't want to double up yet. The only time you start doubling up on the bus is once all the seats have one person in it, right? So it's the same exact principle of Hund's rule. Electrons don't want to double up unless they really have to, all right? So, yeah.
Yeah, so that's that. These are this Paul's exclusion principle, alpha principle, and Hund's rule. This will be important once we discuss over quantum numbers. We'll get to those in a bit.
So,
wait, I can't explain these now.
What?
I gotta do the whole what it is.
Yeah, so we got 9 minutes left. We still have to go through what N, L, M sub L, and M sub S means. And as I don't think we are able to explain this in 9 minutes without letting y'all go into the weekend confused. So I feel like the best thing we do right now is call it a day, because this is something that I'm going to need to start from the very beginning of a little TA recitation session in order to teach y'all, okay? Because again, this is something that it takes a lot of explaining, and I don't want to have to rush it in 8 minutes and then you go into the weekend like, oh my gosh, I was just understanding everything on that worksheet and then they slap me in the face with quantum numbers. So we're gonna do y'all a favor and let y'all go on to your weekend already. We appreciate everyone that came to our session today. We all know that y'all just want to get your weekend started, but we appreciate y'all putting in the effort and work to, hopefully do well on this next exam. But yeah, so
take these 9 minutes, enjoy your weekend. Yeah, we'll be hitting the ground running with quantum numbers on Monday, 5 p.m., same room. So be ready.
How many formulas do we have so far? Let's see. These are the ones that I believe we have so far.
Yeah, so in total, there are 1, 2, 3, 4, like 5-ish formulas. And I don't think I think these are all you need to know, right? I don't think the formulas after this, or there aren't any formulas after this.
I don't believe so. I think.
What's if I think of something?
I'm trying to think. There's like a Schrodinger equation, but you don't need to know that for this class unless you take PChem 1 or 2.
It's pretty advanced for, yeah. Or if you do like computational chemistry, you also have to know Schrodinger's equation. All the calculations you do are based on that, but yeah.
Yeah, so this is all stuff that you should know for sure. Constants involved. I didn't put the speed of light because, let's see, for the last question, when I put the equation in calculus, it gave me 9.8 10 to the 57.
Oh, it's probably because you put like a negative somewhere near like powers. So in the denominator, you could have put like, I don't know, 10 to the plus 24, and that probably could have gave you something that, or some like 57 number. That's at least my guess, but I don't know what you put in calculator because I can't see it.
Really quickly, for the Hund's rule, there's a chance that it could or that one could be empty, right?
So
yeah.
Yeah, so like let's see. Nitrogen has 5 valence electrons.
See it, Daniel.
So nitrogen looks like this. It has its 2s orbital completely filled, and then it has 3 electrons here. But carbon would look something like this, where it just has these 4. So it can have an empty one and 2 that are not completely filled.
And you'll learn that that's not actually the case with carbon, but still, yeah.
But as of right now, we haven't learned about hybridization. So
how does that make sense? All of them are supposed to have at least one before you put the pair.
Because this one's lower in energy. So the 2s is lower in energy, which is why I drew it down here. Yeah, so you always fill the
plus like orbitals in the same energy level.
So that's why 2s gets filled first before you go into 2p. So you fill 2s because why would you want to add another electron here if this is higher in energy? You would fill a 2s first, and then you would fill this one, and then that one, and then that one. And if you have another electron, you double it up. You start doubling it up here, and then here, and then here. It also always has to be in that order from left to right. You can never hop around like this, or you don't start from right to left. It's always left to right. Interesting stuff, huh?
All right, Mohammed, I see your problem. So what you did was you put 10 to the positive 34 for Planck's constant, and Planck's constant should be 10 to the negative 34. So that's probably where you made the error.
That's pretty. How was the session? Oh, pretty good. It was pretty good reviews. Anybody have any more questions?
This guy's so good. Oh, yeah.
All right. Well, y'all can have a good weekend. If there's any questions, feel free to stay and ask them. Jonathan?
You started again, bro. What's up?
How's your spaghetti?